All right, let's talk about one of the weirdest and honestly coolest parts of math, topology. It's this world where you can stretch and twist shapes, and in doing that, you uncover these hidden rules that connect everything. And I mean everything, from your coffee mug to the entire universe. Okay, so let's just dive right in with the most famous and maybe the most mind-blowing idea in all of topology. You ready for this? A topologist will look you straight in the eye and tell you that a coffee mug is exactly the same as a donut. So how? I mean, seriously, how on earth can those be the same thing? One's for coffee, the other's a snack. But yeah, to a topologist, they're identical. To get why, you basically have to forget everything you learned in high school geometry. This is why they call it rubber sheet geometry. Just imagine, every object is made out of super stretchy clay or rubber. In this world, we don't care about things like length or angles or how far apart things are. The only things that matter are the properties that stick around after you've stretched and twisted and squished the object all over the place. The one big rule: you can't tear it and you can't glue bits together. Okay, so to really build this new kind of geometry, we've got to go deeper. We literally have to throw out our rulers and come up with a whole new way of thinking about what it means for 2 points to be close to each other. And this is where it gets really interesting. We're moving from a world of numbers and measurements, what mathematicians call a metric space, to a world of pure structure. In a topological space, nearness isn't about distance, it's more qualitative. It's about being in the same neighborhood. And these neighborhoods, which they call open sets, are the key to understanding everything without ever picking up a ruler. So what exactly is an open set? Don't let the name scare you. It's really just a way of drawing a circle around a bunch of points and calling them a neighborhood. It's the absolute fundamental building block. And the complete set of rules for how you're allowed to draw these neighborhoods, well, that defines the entire space you're working in. It's like the constitution of that universe. And you know what's incredible? The entire foundation of this massive field of math rests on just 3 simple rules. That's it, 3 axioms. First, the whole space itself and the empty set, they're always considered neighborhoods. Second, you can smush any number of neighborhoods together to make a new, bigger one. And third, if you have a finite number of neighborhoods, the area where they all overlap is also a valid neighborhood. That's the whole game. Everything else in topology is built from these 3 ideas. All right, so we've got our new definition of space. But what about the transformations? What are the actual official rules for doing all this stretching and bending? Let's get into it. The big, fancy word for this is a homeomorphism. And all that means is it's the official mathematical rule for stretching without tearing. If you can find a smooth, continuous function that maps one shape to another, and you can find one that maps it back perfectly, then boom, a topologist will tell you they're the same thing. They are homomorphic. So let's bring it back to the mug and the donut. What's the one property they share that survives this whole process? It's the hole, right? The coffee mug has one hole, the handle. The donut has one hole, the center. You can imagine squishing the cup part of the mug down and stretching the handle around until it becomes the donut. The hole is preserved. And because of that, they are, topologically speaking, identical. But this is way, way bigger than just mugs and donuts. This whole idea of finding properties that don't change, what we call invariants, is so powerful we can actually use it to create a complete library of every single possible 2D surface, like all of them. To do that, though, we need a tool, a way to tell shapes apart for sure. And the most powerful tool in the box is something called the Euler characteristic. It's this magic number you can calculate for any shape. You basically draw a grid on it, and then you count the vertices, subtract the number of edges, and add the number of faces. The number you get is a topological invariant. It will not change, no matter how much you stretch that shape. So, let's take a sphere. You can draw any kind of grid on it you want. Triangles, squares, a total mess, doesn't matter. Count up the vertices, subtract the edges, add the faces, and you will always, always get the number 2. It's a fundamental property of the sphere. But now, let's do the same thing for our torus, the donut. You run that same calculation, v minus e plus f, for any grid on its surface, and you always get 0. And that right there is the proof. 2 does not equal 0, so you can now say with absolute mathematical certainty that you can never, ever turn a sphere into a donut without tearing it. And this is the beautiful payoff. Look at this. It turns out you can classify every single possible closed surface in the universe with just two pieces of information, that Euler characteristic we just talked about, and whether it's orientable, which is basically just asking if it has two distinct sides, like an inside and an outside. You see the sphere, genus 0, characteristic 2, the torus, genus 1, characteristic 0. It's just a perfect, complete classification. So elegant. Okay, now we get to the part that's truly going to blow your mind, because these abstract numbers, they're not just for neatly sorting shapes in a math textbook. They have real, physical, unavoidable consequences in our world. I want you to meet my favorite theorem in all of mathematics, the hairy ball theorem. And yes, that is its real name. The theorem says, simply, that you can't comb the hair on a hairy ball flat everywhere. It's impossible. You are guaranteed to have a cowlick, a point where the hair sticks up, or a bald spot. There has to be a weird point somewhere. And why? What's the reason? It's the Euler characteristic. It all comes back to that number. A bigger theorem proves that the number of cowlicks or bald spots has to add up to the Euler characteristic of the surface. So, for a sphere, since the number is 2, it has to have a cowlick. But for a donut, whose number is 0, you actually can comb a hairy donut perfectly flat. The underlying shape literally dictates the physics you can do on it. This deep, profound link between a shape and what's possible on that shape, well, it leads us to one of the most powerful and useful theorems in all of math. It's called the Brouwer fixed point theorem, and it's easier to understand than it sounds. Think about stirring your coffee. As long as you do it smoothly, no splashing. This theorem guarantees that there is at least one single coffee particle that ends up in the exact same position it started in, always. There must be a fixed point that doesn't move. And this is not just some cute party trick. This is a huge deal. This is the theorem that proves that stable equilibrium points must exist in complex economic models. It's used to show that solutions exist for crazy hard differential equations. It's a cornerstone for proving stability in all kinds of dynamic systems. So all of this leaves us with one final enormous question. We've just seen how the basic fundamental properties of a shape can literally force certain physical outcomes. So if that's true for a hairy ball, what does the topology of our entire universe say about the fundamental laws of physics? What secrets are hidden in the very shape of reality itself?